In today's video, we'll learn about the three methods of heat transfer. The first method we'll look at for heat transfer is conduction. And we see that conduction causes molecules to vibrate about their equilibrium position, creating collisions with other particles that radiate out, causing the energy transfer to amplify through the substance. This can only occur if there is a difference in temperature between the two parts of the conduction medium. So we see that the rate of energy transferred by conduction is from a concentration of higher temperatures to a concentration of lower temperatures. And we can calculate the rate of energy transferred to our equation that our power is equal to K, which is our thermal conductivity constant, which is dependent on the material of use, multiplied by the area, multiplied by our hot temperature minus our cold temperature divided by the length or sometimes the thickness of our material. So since K is called the thermal conductivity, we see that good conductors have a large thermal conductivity while good insulators have small thermal conductivities. Heat transfer through convection. And this type of transfer is the transfer of energy by the movement of a substance. So for example, if we have a fire, the fire heats the air, which causes the air to rise, coming in contact with the surface above it, causing that surface to change temperature. And finally, our third type of heat transfer is radiation. Radiation transfers its energy continuously in the form of electromagnetic waves due to thermal vibrations of their molecules. And this type of energy transfer does not require physical contact. So the heat we feel off light bulbs are actually light waves, and the same applies to the fire or even to our sun. We can measure the rate at which an object radiates energy by looking at Stefan's law, which states that the object radiates energy proportional to the fourth power of its absolute temperature. Or once again, P is our power in watts, is equal to sigma, which is Stefan Boltzmann's constant, which has a value of 5.669 times 10 to the negative 8th watts per meter squared times Kelvin to the fourth power, and then multiplied by A, which is our area, times E, which is a constant called emissivity, which varies between objects from a value of 0 to 1, and our temperature measured in Kelvin taken to the fourth power. And we can calculate the net energy gained or lost each second by an object by multiplying sigma times our area multiplied by our emissivity times our final temperature to the fourth power minus our initial temperature to the fourth power. When radiation energy comes in contact with an object, it can either be absorbed or reflected. And an ideal absorber, this object is defined as an object that absorbs all of the energy incident on it, and that its emissivity will be equal to 1. And this type of object is called a black body, an ideal radiator of energy. Well, we have reflectors. An ideal reflector is an object that reflects all of the energy incident on it. So its emissivity is equal to 0, and this type of object absorbs none of the energy incident on it. So if we look at our first example, we see we have a glass window pane in a home that has a thickness of 0.62 centimeters and has the dimensions of 1 meter by 2 meters with a thermal conductivity of 0.8, whereas on a certain day the indoor temperature is 25 degrees Celsius and the outdoor temperature is 0 degrees Celsius. What is the rate at which energy is transferred by heat through the glass? So in part A, we're asked to find how much energy is going to be lost through the window pane. So we summarize the information we're given. We're given that the thickness of the window, which we'll write as the length, symbolized by L, as 0.62 centimeters. And we're given that the area of the window is 1 meter by 2 meters. And our thermal conductivity constant for this material will be 0.800, and that our temperature at a higher concentration is equal to 25 degrees Celsius, while our temperature at our lower concentration will be equal to 0 degrees Celsius. So since this type of heat transfer is the transfer of energy through conduction, we can use the equation that states that our power is equal to our thermal conductivity constant multiplied by area times our change in temperature divided by L. So we know that our thermal conductivity is equal to 0.800, and that our area is 1 meter times 2 meters, which will give us an area of 2 meters squared, multiplied by our hot temperature minus our cold temperature, which will give us a value of 25 degrees Celsius, divided by the thickness of our window pane, which after we convert to meters will be equal to 0.0062 meters. And so we can calculate the power of our heat, which will give us a value of 6,451 watts. In part B, we're asked how much energy is lost through the window in one day, assuming the temperature inside and outside remain constant. So the energy lost can be taken from our equation that relates power to energy, as power is equal to energy divided by time. We can rearrange the equation to solve for our energy, which will give us a final equation of power multiplied by time. We solved for power in part A, and we need to get our times in second. So we know that for one day there are 24 hours, and that for 1 hour there are 3,600 seconds. So if we multiply this through, see that our hours will cancel and we'll be left in seconds. And we see that there are 86,400 seconds in one day. So now we can plug in our values to solve for our energy. Knowing that power is equal to 6,451 watts multiplied by amount of time of 86,400 seconds, we see that the total energy that is lost through the window pane during one day is equal to 5.6 times 10 to the 8th joule. In our second example, we're given that a wood stove is used to heat a single room. The stove is cylindrical in shape with a diameter of 40 centimeters and a length of 50 centimeters, and it operates at a temperature of 477 degrees Kelvin. If the temperature of the room is 294 degrees Kelvin, determine the amount of radiant energy delivered to the room by the stove each second if the emissivity is equal to 0.92. So we're given the area of our stove is a cylindrical shape. We know that the area of a cylinder can be calculated by taking 2 pi r times our height plus 2 times pi multiplied by our radius squared. We can solve for our area, which we can plug in our values, knowing that 2 pi times our radius, which we're given the diameter. If you divide that by 2, you see that our radius is 20 centimeters, and after we convert it to meters, see our radius will be 0.2 meters multiplied by the height, which is given to us as the length of the cylinder of 50 centimeters, which converted to meters will have a value of 0.5 meters plus 2 pi, our radius, squared will actually have a value of 0.88 meters squared. And if you didn't know the equation for the surface area of a cylinder, you could think of a cylinder as having a top and a bottom, which are both circular, and the height of the cylinder, when unwound and flattened, would give us the shape of a rectangle. So we can relate that the area of a circle is pi r squared, and since we have two of them, we would have 2 pi r squared, and we have a rectangle with a height, which is given to us, and that the width of our rectangle is the same as the circumference of our circle. And we know that the circumference of a circle is 2 pi r. So with our width being 2 pi r and our height, we can solve for the area of our rectangle, and then we can add the area of our rectangle plus the area of both our circles to get the total area of our cylinder. So now that we know the area, and we know where our energy is transferred through radiation, we're going to assume that we're going to have to use Stefan's Boltzmann's constant, which has a value of 5.669 times 10 to the negative 8th. And our emissivity is given to us with a value of 0.920. And our temperature at higher concentrations is equal to 477 degrees Kelvin, while our temperature at a lower concentration is equal to 294 degrees Kelvin. And since our energy is being transferred through radiation, we can use the equation that states that power is equal to sigma multiplied by our area times our emissivity multiplied by our temperature at higher concentration to the fourth power minus our temperature at a lower concentration to the fourth power. So we can plug in our values. Since we know that sigma is our Boltzmann's constant, which has a value of 5.669 times 10 to the negative 8th, and that the area of our cylinder is equal to 0.88 meters squared, and our emissivity has a value of 0.920 multiplied by our temperature at a higher concentration of 477 degrees Kelvin to the fourth power minus our temperature at lower concentration of 294 degrees Kelvin to the fourth power. So when we multiply this out, we see that our power will give us a value of 2.03 times 10 to the third joules per second, which is also the units for watts. But we're asked for how much energy is delivered to the room. So given our equation that power is equal to energy over time, and we rearrange our equation to solve for our energy, we know our amount of power and over a time of each second. So we see that our energy will be equal to 2.03 times 10 to the third joules per second multiplied by 1 second. So we see that our seconds will cancel out, and that the total energy that we'll be left with will have a value of 2.03 times 10 to the third joules.